Hi there, welcome back to the formulaic approach. Now in this video, we are going to talk about alkanols. They are commonly called alcohols. So like we have been doing, we are going to do it up from the scratch, such that O-level students and A-level students can, benefit from it and they can catch up with it. But in the meantime, for math students, I've been talking about this textbook, do well to get it. It's going to help you. It contains questions from national and international exam. And I've said it's like a teach yourself textbook. So I also got mine. So you can reach out to me on that WhatsApp number, and then I'll send you the number of the person I got it from. So let's go to alkanols. Now let's give a general definition first. Alkanols are they are not hydrocarbons. Okay, they are not hydrocarbons. They are organic compounds with hydroxyl group. They have the hydroxyl group as their functional group. Hydroxyl group, functional group. Is that okay? So that is, they have the OH group as their functional group. So which gives them a general formula that looks like this. A general formula. Their general formula, keep in mind, is born on the general formula of alkane, of course. So if I put it that way, then I'll write CnH2n plus 2O. Is that clear? Or the correct, the general way we write it is actually, this is the most preferred way we write it, Cn plus 1, then OH. Now, the reason why we prefer this way, this one shows the molecular, this is the molecular formula, okay? This one shows the atoms that are there. This one is primarily to depict that the OH group is the functional group. So in that wise, this one, which represents the alkyl group, this is the alkyl group, is written like this, alkyl group plus OH, that is ROH. So this is their general formula, primarily. Right? So now that we know that, the most important of these alkanols is ethanol, which we primarily discuss. The simplest, of course, is the methanol. So there is methanol, which is the first member of that group. We're going to discuss the homologous series now. Ethanol and methanol. This one is called wood spirit, okay? This is called wood spirit. Now, this one should not be consumed because it causes blindness. So, but of course, this is the most important one because this one is, this one has a wide range of uses, and we are probably going to discuss the uses. So in this video, we are going to go through, after definition now, we are going to talk about their classifications. So let me just put this here so that we'll know what we want to talk about. We're going to talk about their classifications. We'll talk about their, after classification, let's talk about their physical properties. In their classification, we'll talk about their tests. So then we'll talk about their physical properties. Let's talk about their physical properties. Then after talking about their physical properties, let's move to their method of synthesis so that we will now talk about their chemical properties. So with this list, we would have exhausted classification. Okay, we should also talk about their IUPAC nomenclature, okay? IUPAC. So after classification, then physical properties, then synthesis, then chemical properties, and maybe that will be it. That's what we've been doing other organic compounds. So, or maybe we'll talk about uses, But so you have to really pay attention to these physical properties, classification, physical properties. You see these first four that I listed here. You have to pay rapt attention. All right. So now let's begin. Now, let's talk about the classification first. Classification of alcohols. Classification of alcohols. So it's either you call them alkanols or alcohols. Now there are two groups. There are two bases for their classification. The first basis is based on their degrees of substitution. And the second substitution, okay? And the second basis is based on the number of functional group OH attached. So the number of OH attached will, is also used to classify them. And the reason why it is a different class from these is that you see these ones have a different kind of modification in their behavior, in their properties over this one. Do you understand? So that's how we separate them. So based on their degrees of substitution, we have the primary alcohols. You see us write it as 1 degree. And we have the secondary alcohols, like second degree like this. And then we have the tertiary alcohol. There's no quaternary alcohol because you know why. So now, primary alcohols are alcohols that have the carbon that bears the OH. Now, first, keep in mind that the carbon that bears the functional group is called the what? The alpha carbon, okay? The alpha carbon. So this carbon that bears this OH is in turn attached to, let me bring it down here. So we have primary alcohols. Now the primary alkanols are alcohols that the carbon that bears their OH is in turn attached to one more carbon. Okay? Then it's attached, the rest is now hydrogen. The remaining things that are attached, the remaining atoms attached to it are hydrogens. Is that okay? So we can easily write, since it's just one carbon, we can easily write R group here. Okay, one R group. So if it's CH3, it will just be C that is attached to this carbon bearing the OH. Let me repeat that. The primary alkanol is the one in which the carbon that bears the OH group, the alpha carbon, is attached to one carbon only, with the remaining attachments to it, the remaining atoms surrounding it being hydrogen. Then the secondary alkanol is the one in which the carbon that is bearing the OH group, is attached to two carbon atoms. Okay, so then the remaining thing surrounding it is just one hydrogen. So then the tertiary alkanol, is the one in which the carbon bearing the OH group is attached to the first carbon, a second carbon, and a third carbon. Is that okay? So it is tri-substituted tertiary. That's the way to remember it. Tertiary alkanols are tri-substituted. Secondary alcohol are di-substituted. Primary alcohol are mono-substituted. So meaning that one methyl group, one R group is attached for primary, two is attached for secondary. That's the way to think about it too. It's just one R group you will see with primary. That's why it's 1 degree. Second degree, two methyl group attached to the carbon. Attached to the carbon bearing this. Is that okay? Then tertiary alcohols are the one in which there are 3 R groups attached to the carbon bearing the hydroxyl group. Now, why do we separate them? The reason is because they have different reactions. Okay. Now, this is the test for alkanol that we have discussed later. The test for alkanol is this test that helps us to separate between these 3. Okay. Now the test uses Lucas reagent. Okay. Lucas reagent, and Lucas reagent is just zinc chloride and HCl. Okay. So what happens is that if I put a primary alkanol, so let's put a primary alkanol here, plus a Lucas reagent, now what you see is no reaction. No, not like it's no reaction actually. It's actually that the reaction is very slow. It is primary. The reaction is very slow, so much so that turbidity does not appear after a long time. So as much as maybe later than 30 minutes. That is, now what we want to see is that when we react this alcohol with this Lucas reagent, turbidity, that is cloudiness, okay? So very slow turbidity when you react this one. So that turbidity is cloudiness, like I said. So with alkanols, when you mix alkanol with Lucas reagent, very slow turbidity is seen. Okay, but if you react this guy with it, secondary alkanol with it, what you see is moderate turbidity after some 5 minutes. Okay, so this is very slow, as slow as greater than 30 minutes. Okay, while here turbidity shows only after 5 minutes. 5 minutes after which turbidity will be seen. But if you react a tertiary with this guy, if you react tertiary alkanol with this guy, with Lucas reagent, okay, I'll just use LR to represent Lucas reagent, you will see turbidity immediately. There is immediate turbidity. Immediate turbidity. That is, the solution will go cloudy immediately. If it is primary alcohol, if it is tertiary alcohol, the solution goes turbid immediately. If it's secondary alcohol, the solution goes turbid only after 5 minutes. So you see it's quite slow too, but very slow is the primary alkanol. So that's how we distinguish between them. Now let's now talk about this classification. Now this other classification splits this guy, alkanols, into monohydric alkanols, and dihydric, and trihydric, and polyhydric. So now what does this mean? Now monohydric are the ones that have only one OH group. Is that okay? Then dihydric, we have two OH group. Then trihydric, they will have what? Three OH groups. Then polyhydric, we have what? Greater than 3 OH group. So that is how we classify them. Let me give you an example of monohydric. Let me give you examples here. So for monohydric alkanol, okay? Monohydric alkanol is example is ethanol. So for example, methanol will look like this. Methanol will look like this. CH3 then OH, isn't it? So that is methanol. So this is monohydric. Why? Because that's only one OH group. Ethanol as well. Ethanol will look like this. So this is what? Ethanol. Okay? So this is going to have what? One OH group as well. Is that okay? So we can easily draw this as OH like this. This is ethanol here. This is ethanol here. Is that okay? Now, that's monohydric. So for dihydric, an example is what's it called now? Glycol, the ethane 1,2-diol that is used as an antifreeze. So that is going to look something like this. So we have OH attached here and OH attached here. So that's C single bond C, then OH attached here, H. You know, the reason why I usually try as much as possible to write things like this is because, you know, I've told you before that you O did want to carry the bond. Okay, then this bond will now proceed to H. Because if you put H here, to look like, if you put it like this, OH, and then the bond, it will look like this bond is attached to H and another bond goes to O, which is wrong, okay? So that's why I try as much as possible to put it this way. So this guy here is ethane 1,2-diol. Okay, speaking of the naming, okay, let me first give you the examples. Then there's the trihydric. The trihydric is, an example is, if it's trihydric, it means it must have at least 3 carbons, right? It must have 3 carbons. So that example is this guy that is gotten from saponification reaction. That is propane 1,2,3 triol. So that's going to look like this: OH, OH, and OH. So this is propane, propan 1,2,3 triol. Okay? So there will be 3 OH groups attached like this. Is that okay? So you can see 3 OH groups attached. Okay? Then the polyhydric include our sugars like fructose, glucose. So those guys. So for example, let me draw fructose. Fructose is going to look like this. So this guy, you will notice the degrees of substitution of this guy, right? You can see OH is attached at many points. You understand? Several points there. OH is attached at several points there. See OH here, OH here, OH here. So it is a polyhydric. It is polyhydric. This, in case you don't know, is fructose. So that's fructose. Is that okay? This is what is called the Hayward projection. But I'll show you a thing or two here. We're going to do carbohydrates later, so I will expand on that. Now, so that is classification of this thing. For glucose is also a polyhydric alkanol. I mean, and that's now actually that is why we can produce an alcohol from things like fructose and glucose. Is that clear? I mean, of course, it is not exactly the same family, okay? Because fructose is a ketone, while glucose is an aldehyde. None of them are both alcohols, but they have hydroxyl groups, okay? So they behave like alcohols, so they can have alcoholic properties too. So that's why we can classify them as polyhydric alkanols. All right, so that said, the next thing I want to talk about is, I just claimed it. After classification, we'll talk about IUPAC. All right. So let's talk about the naming. The naming of this one is very, very easy, so I won't stress it at all. IUPAC nomenclature of alkanol is basically you have to know how to already name alkanes. So all you have to do is give priority to the hydroxyl group. In a case, of course, where the groups that are there are not higher, okay? So because of the nomenclature sake, I'm going to give you the different groups again that we can have. We can have what is called alkanol. So as you will see in this molecule, for example, this is an alkanol. This, however, is an alkanol. And this is an alkanol. What if we now have both of them? Both double and triple bond. What if I have these molecules? So how do we name these ones? So for example, how do we name this? We simply count the priority is given to this OH group, right? So we come here 1, 2. We omit the guy, the functional group at the second carbon. So 1, 2, 3, 4, 5, giving us a family name of pent. Okay? Pent. Now you can see that it is on carbon 2, right? So pentan 2-ol. Is that okay? Now, why is it an 2-ol? And because it's a single bond all through. Now, another way this was named initially was 2-pentanol. 2-pentanol, to show us that the position of the 2 is the position of the ol or OH group is what? 2. However, keep in mind that the ol is used to replace E in alkane. Is that okay? So OL is used to replace the E and alkane. So instead of 2-pentane, it's now 2-pentanol. So that OL is what signifies that it is actually an alcohol. All right, I'm sorry I didn't mention that. So, for example, if I put OH here as well, okay, so they are now alkanols all together. Now look at this one. Let's name this one here. The name of this guy here is going to look like this. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Now, which direction do we follow? Of course, we are going to follow this direction because our priority will be on OH. If you don't know how to prioritize functional group, I will link a video in the description where I talked about 30 things you must know in organic chemistry before you take organic chemistry. So make sure you see those videos. So, like I said, priority is given to OH. So since priority is given to OH, we're going to name in this direction. We'll meet it at 2 again. So since they are meeting it at 2, it gives us hexane 2 again. But now is it an or n? Now because there is a double bond here, this becomes hexane 2-ol. Is that clear? This is hexane 2-ol. The position of the 2 of the n has to be specified. So this will be in old IUPAC, it will be 1, 2, 3. That will be 3 hexane 2-ol, or we say hex 3 and 2-ol. Okay? Keep in mind we have consonant, vowel, consonant, vowel. So that is that. Hex 3 and 2-ol. Now, how do we name this guy? Now, to name this guy, the same way we are going to count from 1, 2, 3, 4, 5, 6, 7. However, if we go like this, 1, 2, 3, we'll meet this one at 3. But because when we come like this, we'll meet the priority at 2, we're using this. Is that clear? So because our priority is this guy. So this is going to be 7, that's hept. But there's ein here, there's triple bond here. So it becomes hept 1, 2, 3, 4. We'll meet the triple bond on carbon 4. Hept 4 in hept 4 ein. Is it ein or in? Hept 4 ein. Then hept 4 ein 2-ol. Is that clear? Or 4 heptene 2-ol. 4 heptene 2-ol. Is that okay? So these are the same. Is that okay? Both of them are the same. This one is more recent. Okay. Now how do we name this? We're going to go 1, 2, 3, 4, 5, 6. Now actually, the priority would have been given to this guy. Okay, because it's at the beginning here. But because OH is attached here, that's the only problem. So this name will now become 1, 2, 3, 4, 5, 6 carbon. That will be hex. Now, hex 1, 2 and 3, 4, 5, 2 and 5 in X2 and 5 in all. Because why is it in all? Because OH is at number 1, so we don't need to put the 1. So if, whether we put in 1 all is the same as in all. Is that okay? So this is correct. So that is nomenclature. How about we have it that is substituted? Of course, we do it the same way, just like we did here. Just carbon 1 and carbon 2. That will be ethane 2,1,2-diol. But keep in mind, notice that I had to put E here, right? Not ethane 2-diol, 1,2-diol, because this is a consonant. There must be we cannot have consonant or vowel. It has to be vowel consonant or consonant vowel before, so that you don't. If you claim this, you might think it's ethane 1,2-diol, but it should be ethane 1,2-diol according to IUPAC, because consonant vowel should be here, then consonant here. Is that okay? We cannot have double vowel and double consonants like that. So that is it on IUPAC. Now let's quickly talk about the we've talked about naming. Let's talk about their physical properties. Physical properties? Let's talk about their physical properties. Is there anything about this? No. I've talked about their classification, so let's talk about their physical properties now. So keep in mind this Lucas test. The tertiary alkanol goes turbid quickly, while the primary alkanol goes turbid very slowly, and secondary alkanol goes turbid moderately slowly. Is that okay? So let's go to the physical properties now. Physical properties. Now, generally, we are going to be talking about generally, and then be specific to methanol and ethanol, because those are the two most common alcohols. Okay, so physical properties, generally they are colorless, okay? They are colorless, but they have a characteristic smell, okay? Their smell is smell of fermented substance, okay? So they have a characteristic smell, which is of fermented substance. Then they are, so this is now their most important physical property that you are most likely to be tested on. That is their boiling point. Now you see, their boiling points generally are high. They generally have what? High boiling point. So now, relatively, we say their boiling points are higher than their corresponding alkanes. Is that clear? In fact, some lower alkanols even have greater boiling points than higher alkanes. I'm going to show you how. So, for example, I said boiling point higher than corresponding alkanes. That's the first thing. But then I now said that, for example, look at this guy. Methanol, for example. Methanol has a boiling point of about, I can't remember, but ethanol. No, let's use methanol. Methanol has a boiling point of something around 60 something, 60, I can't remember, but it's about 60 something, okay? So let's just say 60. The one I remember is for ethanol, which is 78 degrees Celsius, very close to that of water. So methanol is, methanol has something about 68% degrees Celsius, that's the boiling point. Now, I'll link a video in the description where I've talked about these physical properties of organic compounds. So I think I mentioned other ones, okay? So methanol has, for example, 68%. If you look at ethane, okay? Now, why did I use ethane? This is the reason. You see, methanol has the formula CH3OH, right? What will be the molecular weight? The molecular weight will be 12 plus, that's just the molar mass of everything here, right? 12 is the molar mass of this guy, plus 3 times 1, which is 3, plus oxygen is 16, plus hydrogen is 1 again. So we have 12 plus 3, 15, plus 1, 16, 16, 32. 32. Now, how about ethane? Ethane is C2H6. That is 6 plus 12, that's 24. 12 plus 12, that's 24, plus 6. So now ethane has molar mass of 30, molecular weight of 30. So you can see it's very close, right? Very close. But the boiling point of the thing, even with the fact that it has 2 carbon atoms, that is 1 more carbon atom than this methanol, is minus something. I think minus 80 something, maybe minus 89 degrees Celsius or so. So you see, it is minus something, that's my point, that the methanol that is very lower in its own series is having a greater boiling point than methane. Even butane has a boiling point of about minus 40 something, butane. So you can see butane has 4 carbons. Look at butane, for example. Butane has C4H10. So that's going to be 10 plus 4 times this, 48. So that becomes 68 and 58. So by the time so the molecular weight is almost double methanol. Yet methanol has a higher boiling point than this guy. Now, what is the reason? So the reason for the high boiling point, the generally high boiling point of this guy, for example, we said ethanol. Compare that of ethanol now. Compare ethanol to ethane. Ethanol has boiling point of absolute boiling point is 78 degrees Celsius. Now, if you calculate the molecular weight of this guy, ethanol is C2H5OH. So 2 that is 12, that's 24, plus 5, that's 6. 6 plus 2 plus 16. 30 plus this, 46. Okay? So the molecular weight is 46, while the molecular weight of this guy is 46, while the molecular weight of methane is 30. Albeit this is smaller in weight, okay, but they are corresponding in the series, right? So if they correspond in the series, their property should be close, right? But actually, it is such that ethanol is way, way higher in boiling point than ethane. Like I told you, that of ethane is about minus 89 degrees Celsius. Okay, so that is very, very wide gap. Okay, so that's why we have to discuss their boiling point. Now, what is this thing that makes their boiling point high? Okay, so their high boiling point is due to what? High boiling point is due to presence of hydrogen bond, and dipole-dipole interactions. So they are intermolecular forces. That's what I'm just driving at. They are intermolecular forces. I will link a video in the description. I talked more about the intermolecular forces. The intermolecular forces are stronger than those that are available in ethane. So the only intermolecular force that are available in ethane is LDF, London dispersion forces, or van der Waals forces. Okay, van der Waals forces. They are the only ones available in ethane, and they are the weakest intermolecular forces. But with alkane, with our methanol or alkanols generally, they have hydrogen bond and dipole-dipole interaction. And keep in mind that hydrogen bond is the strongest intermolecular force. Now, actually, relative to when you compare it to covalent bond and electrovalent bond that we have discussed before, it is not as strong, okay? Hydrogen bond is not as strong as them. It's just that in intermolecular forces, this one is still the strongest when you compare. So, because of that, because of the presence of hydrogen bond and dipole-dipole interaction, some energy will first be used to break the covalent bond, and then the excess energy, some more energy will not be needed to break the hydrogen bond. And they are many. So that's what essentially increases their boiling point. Now keep in mind that polyhydric dihydric alkanols will have a greater boiling point than monohydric. Okay, so why? Who can tell me already? That is especially because these ones have two OH groups. So because of that, they have two more centers for coordination of hydrogen bond and dipole-dipole interaction. If you don't understand that, watch the two videos I will link in the description. So there are two more centers than this guy. Okay, for trihydric we have greater boiling point. The trihydric we have than the dihydric. Okay, they will have the trihydric alkanols because they have three OH groups. So they have three coordination centers for hydrogen bond and dipole-dipole interaction. So they have it one more than dihydric. So because of that, they have more boiling point. Another thing is that since they have greater boiling point, as they are like this, so it means that polyhydric will have a greater boiling point than trihydric, and trihydric will have a greater boiling point than dihydric, while dihydric will have a greater boiling point than monohydric. What that also tells you is that as you go down like this, okay, their volatility increases. That is the degree of their disappearance. So it means that these guys are less volatile than this guy, these guys are less volatile than this guy, and these guys are less volatile than this guy. Is that okay? So for example, butane 1,2-diol will not be as volatile as butanol. Do you understand now? Because butane 1,2-diol is it has more OH group. So, and it will give it, the reason for that volatility is because there is higher weight, okay? Higher molecular weight. So higher molecular weight. So you can already see that because of the higher molecular weight, in this sequence rather, the molecular weight also decreases. This one is going to have higher molecular weight than this. So for example, let's use butane 2. So for example, we have butane 1, 2, 3, 4 tetraol. like this, for example, butane 1, 2, 3, 4 tetraol. This is a polyhydric hydrocarbon. This guy is going to have a higher molecular weight than butane 1, 2, 3 triol. While this one is going to have a higher molecular weight than, you already understand it, right? Because oxygen there is going to be added to it, right? That's just, it's just common sense, you understand? Once you understand what I'm talking about here, you can already get what I'm saying. So now let's go to the next thing. Now we understand the physical properties. Now let's talk about their physical properties. Let's talk about their method of synthesis. Let's first talk about the general methods of synthesis. Let me pause the video to clean the board. Now, what are the methods used in the production of alkanols? Now, synthesis of alkanols. Now, I'm first going to talk about their general methods, okay? General methods. Now, the general method that you have to know is the method of hydration of alkene, okay? Maybe I should first list them. Let's talk about the method of hydration of alkenes. So it is such that if I want to prepare, I'm going to use the locus classicus, that is a theme, for example. If I want to synthesize, we can use anyone. Let's use propene. I like to use propene. The reason why I want to use propene is because this hydration usually follows Markovnikov principle. It follows Markovnikov addition. Markovnikov's addition, or WF, whichever one you're spelling. So Markovnikov addition, and that is because of the formation of stable carbocation. I'm going to show you what that means. So for example, let's say we want to use propene, for example, CH3, CH2OH. So we want to let's use propene, I said, right? CH2, sorry. CH2. So we want to synthesize alkanol from this guy. So now it happens in the presence of we say it is an acid catalyzed reaction, okay? And it is basically by the hydration. Hydration means the addition of water to something. Is that okay? The addition of water. So how does water get added to this thing? What will happen is that, so there is also, I said it is an acid catalyzed reaction. So it's going to happen in the presence of maybe H2SO4 or any other strong acid, okay? So by the time you have this, the protons, I'm going to show you what will happen is that this guy is going to form CH3, CH2OH, then CH3. So what happens? Structurally, what you will see is this. It's going to look like this. Okay, so what will happen is that the hydrogen ion from here, this one is going to give us what? Hydrogen ion, right? So this hydrogen ion is going to be attacked by this double bond. So immediately it's attacked by this double bond. The double bond is broken. Once the double bond is broken, okay, which of these product is going to be formed? Now, you know that what wants to be added here is OH minus. This is what wants to be added. So what will happen is that this OH group is the heavier group, okay? So H is going to be added somewhere else, OH is going to be added somewhere else. This H rather is going to be added somewhere else, OH is going to be added somewhere else. Is that okay? You know OH is already floating in the solution, right? Because it's a floating solution. So OH now will now say, will I add on to this guy or add on to this guy? So according to Markovnikov, OH is the heavier group than H. So the heavier group will go to where there is low H. H will go to where there is more H. Is that okay? Hydrogen will go to where there is more hydrogen. So which of this carbon will get the hydrogen? It is this carbon. That's the Markovnikov product. and the OH will come here. Is that okay? Now, that is the easy way of defining that, explaining that. Actually, what is happening is because there's going to be a formation of what's it called now? A carbocation. Okay, I've told you this before. The procedure, the reaction proceeds by an E2 mechanism. Okay, by E2 mechanism, that is elimination by molecular reaction. So what will happen is that the new H group will come and attach to this side, and our OH minus is coming to attack this carbocation, and then this will be the alcohol that will form. Do you understand? This is the alcohol that will form. The reason I said again is that why is OH not attaching here? Is because this reaction requires an intermediate. Okay, this intermediate that is formed is easy to be formed because this is a secondary carbocation. Now, a secondary carbocation is simply a carbocation that is attached to two more carbons. Okay, it is disubstituted. That's how to think of it again. So just like we did for classification of alkanols just now. So this is what will form rather than actually, it is, as I've told you before, it is actually 80% to 20% of this other product. This is another product that is possible. OH being attached to this side with the H coming here and this. But since this is the major product, we call this the Markovnikov product. And this one is the minor product. This one is just 20% that will form that. Exactly. So that is the case for this guy. Now, the degree of formation of the kind of alcohols goes like this. The extent of formation, rather. It is easier to form tertiary alkanols. Tertiary alkanols are easier than secondary alkanols, and secondary alkanols are easier formed than primary alkanols. Primary alkanols are the ones that are harder to form with hydration of alkenes. Okay, they are harder to form with hydration of alkenes. But tertiary alkanols, because it is dependent on that, it is an E2 mechanism. It depends on both the attacking reagent and the formation of carbocation. That's why we call it bimolecular. It depends on this cation and the attacking nucleophile. Okay. So that is that's about that guy. So now, but actually we can form an anti-Markovnikov product. The anti-Markovnikov product will look something like this. Now, I emphasize this on this thing, alkenes too. So maybe you should also see that video on alkene. Now, the anti-Markovnikov product is going to look like this. First, it happens in the presence of it happens in when we are doing hydroboration oxidation. Hydroboration oxidation. So if that is the case, and in the presence of a peroxide, I've told you this before, right? It's called the Karask effect, right? In the presence of the peroxide, that's when this occurs. Then it means that these are a guy. So this time I'm going to draw what looks like this, okay? So you can already understand. So there is any RBH, okay? Our alkyl group plus. Let's use, for example, we can use in the presence of H2O2. So what will happen, of course, there's still water as well. What will happen is that this guy is going to form, rather than form this Markovnikov product, this is the, in fact, this anti-Markovnikov product will be the major product, so that OH comes to attach here and H comes here. Then the minor product, this will be the minor product where OH is attaching here. You see that OH that was supposed to attach, if this were this guy, OH is supposed, this was supposed to be the major product, if it's a Markovnikov product. But this is anti-Markovnikov, so this one will be the major product. This will be the major product. Alright, so that's that for hydration of alkenes. Now, another method of synthesizing alkene generally is we have hydration, we also have reduction, okay? Catalytic reduction. Catalytic reduction of carbonyl compounds. Carbonyl compounds. Now, what are carbonyl compounds or carbonyl compounds? That what you call it. Now, carbonyl compounds are compounds that have C double bond O. So they are either aldehydes and or ketones, okay, or ketones and or carboxylic acids. Carboxylic acids. So yes, carboxylic acids are also reducible. So it is such that an aldehyde, now take note of this one, an aldehyde or an alkanal, that's another name for it. An alkanal will be reduced to give a primary alkanol. Primary alkanol. While a ketone will reduce to give a secondary alkanol. Is that okay? But of course, a carboxylic acid will first reduce to an alkanal. This one is a two-step process. Now, I can actually proceed in one step if you supply a very strong reducing agent. Now, this one will first go to alkanal usually, then before going to primary alkanol as well. Is that okay? So it is such that ketone is one that always gives us alkanal. And if you understand what a ketone is, you know the reason. So I drew a ketone here just now. You know the reason why it always forms a secondary alkanol rather than a primary alkanol. Then we don't use this method for tertiary alkanol usually. So as it is, let me show you. Now we use reducing agents. The reducing agents that we use, they include we can use lithium, aluminum hydride, or sodium borohydride. Okay, so these are strong reducing agents. They supply hydrogen to the guy. So for example, we could have, let's use a ketone like this guy. An example is this guy, propanone. Okay, this propanone. Now, the moment you subject it to heat, it happens in presence of, let's say this guy, LiAlH4, okay? In the presence of dry ether as well and water, what will happen is that this guy will reduce this guy, and on reducing it, is going to form for us a second. Now, notice where the double bond is. The double bond is in between two carbons, right? The carbonyl compound, rather, the carbonyl carbon is in between two other carbons. So it means that the OH that is going to form is going to be in between two compounds as well, two carbons as well. Is that clear? So what will happen is that there's going to be protonation of this guy. This guy is going to abstract. The reaction mechanism is such that this guy will take its bond, use it to attach to another hydrogen, and then that's just the process of the mechanism of the reaction. So and then you form propan. So this was propanone becoming propantuol. Exactly. What if we had this? This is propanal, right? This is propanal. This is an aldehyde, right? By the time you subject this one to heating in the presence of AlH4 or NABH4, either ways, you are going to get an ether. You are going to get you're going to get what looks like this, OH. So do you notice that the OH group is attached to the last carbon, the terminal carbon? So and this is what a primary alkanol, and this is propanol. This one is secondary alkanol. Like I said, ketone, secondary alkanol, and aldehyde, primary alkanol. So, but what if it's something like butanoic acid or propanoic acid? So, if it were, let's use butanoic, or use propanol. If it were butanoic, it would look like this, right? And then we have C double bond O. We usually put that up. O then OH here. So this guy will first revert to this. So this is butanol. So butanol will first go We'll first go to butanoic acid rather. We'll first go to what? Becoming butanal, sorry, and this guy will now go, in the presence of further reducing agent, will go to becoming butanol. Is that clear? So carboxylic acid goes to alkanal and to alkanol. So that is the process of reduction of alkene, catalytic reduction of carbonyl compounds. Now another one that we usually, there is also a general method, but I don't know if it's usually discussed, is the use of Grignard reagent. So we also use Grignard reagent for reducing. Okay, so using the Grignard reagent, Grignard reagent. So I think the process is also catalyzed. I think it happens in terms of a catalyst, but I'll just show you what the reaction is here. So this is Grignard reagent, that is RNGX, right? So now it is such that if you want to make a primary alkanol, you can only use methanol. You can only use methanol with the Grignard reagent. But for every other, but for secondary and tertiary, you can use any other alkanol. Is that okay? You can use any other alkanol. So keep in mind, if you can use any other alkanal. This is also still reduction of carbonyl. So it's also under reduction of carbonyl compounds. Okay? So for example, if I want to obtain ethanol, for example, what will be done is I'll use CH3, for example, RMGX. Let's use Cl here. Then this guy will be added to methanol, which is something like this. How does methanol look? C double bond O. Okay, yes. That's formaldehyde, right? That's the name, formaldehyde. This guy is going to now attach to this guy such that you now have CH3, CH2OH, and that's going to be what? Ethanol. You understand? So that's ethanol. So this is the only way we can manufacture primary alkanol. If I wanted to use propanol, for example, I will attach what here? Ethyl group. So ethyl group here, C2H5 here, then MgCl plus methanol. Keep in mind that for our primary alkanols, use methanol. Because if you use anything greater than methanol, it will give you secondary alkanol or maybe even tertiary alkanol. So to get primary alkanol, use methanol for this process. So then of course, let's make a secondary alkanol. For what I was saying, secondary alkanol will be manufactured via a process that looks like this. Let's use H3CMgCl plus, now we can use C3 C double bond OH. So when we have this, then we're gonna have this guy will come forward so that it becomes CH3 CH2 and CHOH and CH3. Exactly. So this is propanol, propan-2-ol rather, propan-2-ol. You see that? All right. So this guy simply came to the front. All right. Now the next thing is another method of synthesis. So we talked about 3. Let's talk about another one. The other one is I'm still talking about the general methods, okay? We'll still talk about industrial now before we now talk about chemical properties. So another general method of synthesis is, I'm trying to remember now. We use our reduction of alkene, anhydration. Then which other one have we not discussed? Which other one? we also, there's also catalytic reduction of this thing, some cyclos, okay? Some cyclos. So, for example, if catalytic reduction of some cyclo group, some cyclic ketones. So, cyclic ketones like this. Like, if I have something like that looks like this, for example, maybe. So this would be hexanone, cyclohexanone. Now this is the functional group. So go 1, 2, hexan 2, 1. This is cyclohexan, hex 2 and none, hex 2 and none. So if I reduce this using in the presence of platinum catalyst and heat, of course, by the time you react it, you are going to get a cyclic alcohol as well. Okay, so and this will be 1, 2, 3, 4, 5, 6. So this will be hexanol. Do you understand now? So that is another process. It's still reduction. Now, if I remember another one, I'm going to talk about it. But so far, these are the ones I can remember. Now, let's talk about well, keep in mind this Markovnikov process. This is the major process. Now, let's now talk about the industrial process of the industrial methods. Industrial methods of preparation. Now, I'll talk about 2 industrial methods. Actually, on a large scale, the industrial method that is actually used on a large scale is that hydration. Okay, that hydration is done in the presence of, you see, that hydration. Let me first write industrial process. Keep this in mind, that industrial process, that hydration is the one they use for the production of ethanol. Okay, so hydration of ethene is done on a large scale. Okay, in the presence of phosphoric acid, concentration of phosphoric acid, right? And then you're able to with high heat. Okay. So, but another one that we use industrially, this one is for methanol. Let me talk about methanol. And they use, so they will heat coke with steam. So coke with steam will be heated, and you'll get carbon monoxide, okay, carbon 2 oxide, plus H2. Remember that they call this water gas, right? This is called water gas. So now they will also mix this guy, methane. Okay, methane is also heated with water, with steam, not water, please, with steam. Okay, by the time it is heated, you also give this, but this is going to be a mixture of products. Okay, it's going to be a mixture of products. It's going to be a mixture of these 2 products. Now, this one is called synthesis gas. By the time I balance it, now watch. This one is called synthesis gas. Let me balance this. This becomes 6. We will put 3 here. That's 6. So the mixture of these 2 together, you know that I said is synthesis gas. The mixture of these 2 together, now heated with the mixture of those 2 together, now heated with both gases, water gas plus synthesis gas. When you heat them with together in the presence of Cr2O3, okay, the presence of Cr2O3 and a temperature of about 300 degrees Celsius and 200 ATM, 200 atmospheric pressure, then you get methanol. Exactly. So that is one way in which it can be produced. Okay. So if you eat this mixture with water, you get methanol. That's one way they produce industrially. But the one that you are most likely to be asked about is ethanol. So there are two processes of producing ethanol industrially. So let me call it three. Ethanol. You can produce ethanol first from sugar. From sugar, okay? So the sugar we're going to be using here is molasses, okay? Now, we can obtain it from molasses, from sugar. We can also do sugar or beets, okay? Or grape, okay? But what molasses is just a thick syrup or thick syrupy liquid that is obtained industrially from processing companies, that food processing companies. So, for example, when they obtain these molasses, you might think that they should extract the sugars back, okay, because it contains sugar. That's the major thing I want to talk about there. So, but actually, they found out that it was not economical. Okay, the sugar that will be obtained there will not be able to cater for the process. Okay, do you understand? That is not economically viable. Okay, so for that reason, they will easily convert that molasses to alcohol, which is more economically useful. People buy it for beverages, use it for production of drugs, blah blah blah. So that's why they basically do this. So inside this molasses is added to water, okay? Added to water, and what happens is that it's going to show about 10%, it's going to be diluted to about 10% of its concentration, okay? Such that the sugar will be made available. In this case, is actually about 60% of the whole thing that is the sugar. It contains 60% sugar. Now, right after diluting it to water, then the next thing that will be done is that the molasses will be treated. The molasses will be treated with ammonium sulfate, NH4SO4. So that will be NH4SO4. So NH4 to SO4. This ammonium sulfate, potassium nitrate, and a dilute acid, usually dilute H2SO4. Now listen, you see this dilute H2, if you use concentrated H2SO4, it will hinder the process because you are going to also add yeast. So there are many things you are adding. You are going to also add yeast, then also heat it up. Do you understand? So heat it up. When you heat it up, the reason why if you add a concentrated, the reason why we say not to add why you are told not to add concentrated acid is that a concentrated acid will deactivate the enzymes in this yeast. Okay, so because it's an enzyme catalyzed reaction. It's an enzyme catalyzed reaction. Enzyme catalyzed. But the first one I told you is not enzyme catalyzed. Yeah. So this is an enzyme catalyzed reaction. What are the enzymes that are present in the yeast? Amylases generally are present. Now we have alpha and beta amylases, and they have the common names. Invertase is common in yeast, and zymase are common in yeast. So now what happens is that when this guy breaks down, it's going to break down by the presence, it's going to break down into sugar, okay? It breaks down into sugar. So when you add this guy, you cover it with heat, you cover it for about a week, okay? It's covered for about a week. Then what will happen is that it will have reduced this thing to the sugar. It will have brought out the sugar in. And what is that sugar? The sugar is basically C12H22O11. So I'm not going to deal with the structure here. We'll deal with that later. So this sugar primarily contains, sucrose. This is sucrose, okay? And sucrose is made up of glucose and fructose. So it brings out sucrose. Now what will happen is, on further reaction, This sucrose will now be acted upon by invertase enzyme. So what does the invertase enzyme do? The invertase enzyme is going to convert this glucose, sucrose, break it down to glucose and the component I said, fructose. Okay? Fructose. So glucose is going to be C6H12O6 and this one is also C6H12O6. Okay. I might have to do with structures here. Listen, so that you not think they are the same. They are not the same. See, glucose looks like this. Glucose looks like this. Glucose formula will look like this. This is C12. That will be like 2 of this, 2 of this, something like that. You know, you can balance the reaction, of course. So by the time you get this glucose, I said this glucose, they look alike in formula, but they are not actually the same structurally. So they are structural isomers. So glucose looks something like this. C double bond O. Yeah, it's more like what I drew the other time, but you still see that they are not the same. While fructose looks like this. Okay, this one has double bond here. So this is a ketone. This guy is a ketone. While this guy is an aldehyde. Okay, so this guy is going to have CH2OH. This guy also have CH2OH. Okay, now this one will have OH here, OH here. This guy will have OH here, but then OH here. Okay, then this guy will have OH here, OH here, OH here, here, H, and CH2OH. By the time we count it, you'll see we have 1, 2, 3, 4, 5, 6 H, 6 carbons. Hydrogen is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's count again. You see it's not complete now. It's not complete. It's not complete. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm not counting right here. Okay, CH2OH. I'm sorry. 12. So then O6. 1, 2, 3, 4, 5, 6. Is that okay? Count for this one is going to be the same as well. Then of course, structurally, this convention is called Hayward convention. I said I was not going to deal with structure. Hayward projection rather. Hayward projection. Then I just want you to see the difference, okay? These guys, they cyclize in a process known as hemiacetal cyclization. Just as a note, okay, just put it somewhere. Hemiacetal cyclization. We'll deal with it in our carbohydrate series. So in hemiacetal cyclization, after cyclizing, this guy will form what is called. This is called a pyranose shape. This is pyranose, and this one is furanose. I've talked about this shape too in that introduction to organic chemistry, 30 things you must know in organic chemistry. So make sure you look at that video, watch that video. CH2OH, OH, OH here, OH down here, because the position of the OH is very, very important. It determines whether it is actually glucose or not. It can change its CH2OH, OH. Then H here. Alright, so this is glucose. This is glucose. Sorry. CH2OH. It's supposed to be here. Then here we have OH is down. OH is down here. And H is here. I'll teach you how to draw this shape. It's very simple. You just bend this molecule, then you will know how to position your H and OH, okay? Then this one is fructose. So this is glucose when it cyclizes, and this one is actually called D-glucose. This is alpha D glucose. Alpha D glucose. So we have CH2OH, CH2OH here, and of course we have our OH, 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 H, OH, and OH. So that is going to be OH, OH, H, OH. But basically, what I want you to see is that look at the rings. You see that the rings are not alike, right? The rings are not alike. This one is called a furanose ring. This one is called a pyranose ring. But the point is, This guy becomes this. Now, what now happens? You see this glucose is now our next reactant. So this glucose now comes here. C6H12O6 is now acted upon by another enzyme known as zimase. Okay? Inside, you see, I told you there are two enzymes inside the yeast, right? Two enzymes that are inside yeast, invertase and zimase, and both are forms of amylases. So the zimase guy will now act upon this guy, and then you form C. If you remember the process of your anaerobic respiration, this is the reaction I wrote for you. Do you remember? Simply balance out. So it will form C. This is C2H5OH. This is ethanol. Do you understand now? This is ethanol. So the glucose undergoes conversion for that to what? To that guy. But actually, the ethanol that is obtained in this process is not, the ethanol that is obtained in this process is not, what's it called now? It's not absolute, is it absolute? It's not absolute ethanol. It still has to be rectified. It has to undergo the process of rectification. So the rectification process is just, there are two terms I want you to remember here. The rectification process, I said it undergoes rectification. It is this rectification that makes it rectification, that makes it ready for drinking, as well as makes it concentrated enough so that it removes water. You know, everything's happening in water. So the process of rectification is called azeotropic. Now, azeotropic distillation is a distillation process. Okay, why is it called azeotropic distillation? It's not a normal distillation process. Azeotropic substance is a substance that has the same constituents in different physical states. So if it has in gaseous and liquid states, all the constituents are the same. So because of that, it has to undergo azeotropic distillation, such that this is a special type of distillation. That's what I mean. Such that the water is being removed and it is concentrated. The ethanol is concentrated for drinking, and the ethanol that is obtained in the process is 99% pure ethanol, and that is called rectified spirit. It's now called rectified spirit. So that's that for this guy. Then how about this other guy? The process of the second process, I said we can use sugar and molasses. Then the other one is what we wanted to use starch. So this is 3B now. What we wanted to use starch. Okay, you know starch is present in potatoes, starch is present in maize, starch is present in rice, maize, blah blah blah, barley. So these guys are going to be, you know, the product. So we'll mash them. Okay, we'll mash them and cook them under high pressure. So after mashing and cooking under high pressure, we're able to extract starch out. So that starch extract simply looks like this: C12H22O11 still. Now this, I wanted to show you this, that this guy, sucrose that broke down to this guy is a disaccharide. A disaccharide is a type of sugar. It breaks down into an hexose sugar that is a monosaccharide. This one is also a monosaccharide. Now this one is a disaccharide, like I said, but this one starch here, you see I'm putting N here. Here I put, this is supposed to be, this one is just for balancing, this two is for balancing, okay? But you see this one I put N here, this N is not for balancing, this N is actually a long chain of sugar. Is that okay? So that is, this one is called a polysaccharide. A polysaccharide. So now what happens is that to this starch you add malt. Is that okay? You add malt. And when you add malt, what will happen is that inside malt that is gotten from barley, what will happen is that a certain enzyme known as diastase is inside malt, it will break it down such that you have maltose sugar. And maltose sugar is actually 2C6, 2C12H22 again. What am I? H22, O11. Okay, these maltose again. So these maltose will now undergo conversion. You now add yeast. Okay, it's to this guy you now add yeast. Then the enzyme zimase will now act on it. Diastase we add inside this when you add malt, the diastase will act on it to give you maltose. The maltase will act on it. Maltase will now break maltose down. See, the word "ase" means break, okay? So maltase will break maltose down to give you sugar. So this one actually has 2 molecules of glucose, C6H12O6. Maltose is composed of 2 molecules of glucose. So 2 of these glucose molecules, they will be joined by what is called an O-glycosidic bond. It's a type of bonding, okay? It's called addition polymerization. Just for your knowing, okay? Glycosidic bond. So they are joined by glycosidic bond. So 2 glucoses will be joined by glycosidic bond, and the 2 glucose will now undergo fermentation. So this process here is what you call fermentation. Okay, fermentation. From the action of yeast to this whole process here is called fermentation. Then glucose will now act on it and give you, glucose. Zimase is an enzyme again inside the yeast that will now act on this guy to give you C6, C2H5OH plus CO2. Then this process again will now be rectified to undergo rectification, azeotropic, azeotropic distillation. So that is that on the production or industrial preparation of this guy. Let's now go to the chemical properties. Let me clean the board and pause the video. Now let's talk about the chemical properties or chemical reactions that alcohols undergo. Or can undergo. Now, the first one I want to talk about is basically combustion. So that is the one we normally talk about for all hydrocarbons, all organic compounds, combustion reaction. So when you heat ethanol, for example, our locus classicus is ethanol. So most of the time we'll be talking about it. You heat it with abundant supply of oxygen, you're going to get CO2 plus H2O. Is that clear? When you burn ethanol. Now you balance the reaction yourself, that's C2H5OH plus O2 gives CO2 plus H2O. If you have problems with balancing chemical reactions, I'll link a video in the description. Now, so that's the first one. Now the second reaction is the one of dehydration. And of course, you can already see that we can dehydrate it. Dehydration of alkanol. So, for example, if I have my CH3CH2OH, now I can dehydrate it. Now, the process of dehydration also follows Zev's rule, okay? Follows whose rule? Zev's rule. Zev's rule says that, now in this one is easier, dehydration is easy because we can easily take this guy, how do we dehydrate? We dehydrate in the presence of an acid, catalyst as well, and with a temperature of about 180 degrees Celsius and 60 atm, okay, you are able to dehydrate this. Now when you dehydrate this, what will happen? This guy will be protonated so that it will be a good living group. It will be deprotonated. By the time it's deprotonated, it will leave. So, and this guy, the bond here will also cleave. Okay, the bond will cleave. This guy will leave because it will be protonated. So by the time it gets protonated, it becomes OH2, that's water, right? So it can now leave. So when it leaves, then this bond, this bond will break here, sorry. It's not like the bond will not cleave to this hydrogen. This hydrogen will be abstracted. This one will now cleave. Is that okay? It will now break on this one. So it now form, it is not this hydrogen that will cleave, it's this hydrogen, sorry, this hydrogen now. Then this bond that will break. So we now have CH2 like this, double bond CH2. So we are able to form our alkene back. Ethene. We started with ethanol and we ended with ethene. Ethanol and ended with ethene. So you can already see the process here. Very easy, right? But the thing is that now when you're now giving the one that you have to use Zev's rule for, there are two ways of seeing that Zev's rule. In case you have read the textbook that gave you Zev's rule is the same, okay? Or Zev's rule. I think I prefer this first one though. Now either ways, if I now give you something like this is what I mean now. If I give you something like this, my alkanol is here, but is with an unsymmetric, is it symmetrical now? I think this is unsymmetrical. Unsymmetrical carbon molecule. Now, you see this guy, we want to dehydrate. Now, so the question is now, no, this one is still easy. Let's say the OH were to be here. Because in that one, the bond will form here. So it's very easy. The bond will not come and form here. Exactly. The bond will form here. In that one I drew the other time. What if I now have CH3 here? So the bond, the guy will now choose whether to form here, whether to form the bond here, or to form the bond here. But it's still quite the same. How does it follow Zev's rule? I'm trying to look at how it forms Zev's rule. If it were here, it will be to form between here and here. Okay, Now look at this example, for example. Now look at this. Where will this form? If you choose between to form here, to form the double bond here, or to form the double bond here. So now what will happen? You know this guy, we said it will take place in presence of what? The protic solvent. And this guy will be protonated. By the time the H plus comes and attacks this guy becomes CH3 here, HC. Now this now becomes OH2, right? Because it has been protonated. And OH2 is a good living group. It can live. That is, it can live. Because it's water, so water will live. Once the bond cleaves, it will now form a carbocation. Okay? Now the carbocation will form. Something will happen. There will be a shift. The carbocation shift. The carbocation will shift here. Is that okay? It will shift because of hyperconjugation effect. So it will shift, and by the time it shifts, what will happen is that we'll have HCH3 like this. Now the carbocation will now shift here because this guy has left. There is a carbocation here, and then our H is here. So because of that, the double bond can now form here. Do you understand now? The double bond can now form here. So this hydrogen will now be abstracted in the root. The double bond will prefer to form here than here. This is Zev's rule. Zev's rule is saying that the double bond will form where the carbocation will be more stable, and where will be the carbocation that will form. This carbocation is the intermediate product. This intermediate product. The final product will look like this: CH3, C, double bond, then CH3 here, CH, then CH3. Okay, so when we have a symmetrical, so this one is for symmetrical here. So the carbocation will prefer to form where there is, this is a tertiary carbocation, right? So this is a more stable carbocation than the secondary carbocation that would have been formed there. And even the carbocation was formed there, we have what looks like this. This has only two groups supplying electron density towards it. So it will not be as stable as when the carbocation is here. So that is why that guy is formed there. Now, the next reaction I would like to talk about is the hydration of alkanols. The other one is the last one we'll talk about is esterification reaction. That's my best. That's the one I like the most. And don't ask me why. So we have dehydration of alkanol. So we've treated that. Now the next one is what other reactions? What other reaction? Let me quickly remember. We have oxidation. So before we actually treat oxidation, let's talk about the acidity of alkanols. So acidity of alkanol is seen in its behavior when it reacts with reactive metals. Now, keep this thing in mind. This is the reason why alkanols are not kept in metal containers. Now, the reason is this. Watch this. If I have sodium, for example, react with ethanol, what usually occurs is that this OH bond is broken with hydrogen given off. Is that okay? So sodium displaces it. So it will now form sodium ethoxide, which will look something like this, CH5ONA. So this is sodium ethoxide. Okay, so this shows its acidity, its ability to give away its hydrogen. Do you understand? So in the intermediate, it will form what looks like this, right? The bond will cleave to it because it's more electronegative, and this is its conjugate base. So this will be the conjugate acid. This one will leave because it's a reactive metal. So that's why we don't put this guy in tin cylinders, in tin containers, because it's reactive. Alkanols can react with metals. So that is that. And the other one is now oxidation. Now, first keep in mind that this one is in degrees. So for primary alkanols, they undergo partial oxidation. Okay, in partial oxidation, we add just some KO. For example, it could be in the presence of KMnO4. All those oxidized agents that we use. So these guys will oxidize. Primary alkanol will oxidize to an alkanal. So for example, if we started with ethanol, C2H5OH, by the time it gets oxidized, it's going to, this is why we are drawing it like this, is to show you that it's only the oxygen that is the most reactive that we need there. So it will form this C3C double bond OH. But if it were for full oxidation, on further oxidation, we now oxidize this. So that is full oxidation now. This guy will now get oxidized to C double bond OOH and ethanoic acid. Keep in mind that this one is ethanol became ethanol, right? Analdehyde, and then became ethanoic acid. So you oxidize just the way we did the synthesis. We went from alkanoic to ethanol, then to ethanol. The same way, you can also oxidize ethanol to ethanol and ethanoic acid on further oxidation. What if it were a primary? If it were a secondary alkanol? For a secondary alkanol, we can only oxidize to a ketone. We cannot get anything further. Okay, so for example, if I oxidize alkanol like this, what I will get is propanone, for example. Exactly. So that is the case with oxidation. How about tertiary? Tertiary alkanols cannot be oxidized. Cannot be oxidized. It cannot be oxidized. Okay? That is plus OH now. It cannot be oxidized. Now let's talk about the last reaction of the day. Now keep in mind the use of alkanol. It is used as beverage. It is used, and that test, Lucas test, don't forget, those are the things I want to talk about last. It is used as beverage, as additive, as conservation agent or something like that. Yeah, for preservation agent. Yes. So now the last reaction I want to talk about is esterification from my ester. So we have this, for example. Now the reaction is, what number is that? Number 5. It's called esterification. Now it's very simple. It's a very simple reaction. Now it's also reversible. Now it's basically involves an alkanol reacting with an alkanoic acid to form an ester. Now what is an ester? An ester is a sweet-smelling organic compound that we generally call alkanoids. Okay? So ester plus water. Let me teach you how to do it. It's very simple. Pick any alkanol. I want to pick propanol, for example. This is propanol here, right? Okay? This is propanol here. Now, I want to pick any alkanoic acid I want. Let me use ethanoic acid. That will be CH3. C double on O and OH. Now, do you know what you do to get your ester? Very simple. Don't go to ester's house. Simply stay and do like this. If you want to get your ester, simply stay. Don't go to ester's house. Just come and do like this. Draw an arrow. Then do this. Watch me. Watch me. Do this. Pick this OH here, okay? And pick this H here. What would this form? H2O, right? So come and put here. Plus H2O. Then the rest, do you know what you do? You flip this guy. You will flip it. So when you flip it, no, it's not this guy you flip. It's this guy you flip. You flip this alkanol side. You flip it here. So you rewrite what you have here. Because this is the ester backbone, then this one will now continue bond with, so this bond here will now continue with this guy, C12, C12, C13. H2, C13. You see what I did? I simply brought this guy, brought it here, and came to form one. Then the name, I started with propanol and ethanoic acid. Now, because of the strength of ethanoic acid, this name is going to favor ethanoic. Okay, so it becomes we always name from back to the front. So this is propyl ethanoic. Even if it's an aryl group, aryl groups are benzyl and phenyl. If you don't understand what that is, see my video in the description. It is the same process. Simply take your oic guy, plaster it back, then flip your guy over, your alkanoic group over, and then you're able to form the ester. Is that okay? Esters are generally called alkanoids. Do want to subscribe to the channel. That will be for this video, and click the bell notification to get notified whenever I drop a new video. God bless you.